And then step 2, show this efficiency. Obviously, when I say suitable candidates, if you are doing an LP, so first I make a possible guess situation LP, and then in this next case, left, I said the candidate is indeed the right guess. So first make a guess, educated guess, and show that the guess is the right place and is also the right thing. So what we do in step 1 is establish that there exists a measurable function f I'll make some statements later, such that a subsequence of Fn converges that's the first step that we are going to show, that there is some fellow, at least where I get some point, I have to define that function. So I must know what it is at each point. So that information has to be recovered from the values of the known functions at some point. So therefore, somehow or the other, the values of the known functions must come into the picture in defining the value of this new function. So that's why I say at almost every point, when some subsequence will converge, so I can take that limit as the value of that known function. How do we do this? So we are given Fn is a Cauchy sequence in L. That's the given information. Now what does this really mean by definition? For every epsilon positive, there exists an n epsilon such that n and m greater than or equal to n epsilon implies norm fn minus norm fn. That is the given information. For every epsilon, you can always find a stage beyond which the p norm of the difference of the sequence is always less than epsilon. That is the given information. Now we are going to use this given information repeatedly to construct our function f. So, therefore, for epsilon equal to 1 over 2 to the k, suppose I choose that, k equal to 1, 2, 3, 4, etc. Then for each one of them I will get a corresponding stage where, so let us take epsilon equal to half to start. What does this say? There exists an n1, I will call it n1, I will call it 2 to the power of 1, that power is that index, n1 such that nm greater than or equal to n1 implies norm fn is less than of 1. I chose an epsilon to be. So what it is here is the sequence. That's the sequence. Now what this says is there is a stage n1 and if we choose fn and fm here, then the difference in the norm will be less than half. So that's what it says. Now choose epsilon is equal to 1 by 2 square. What happens? There exists an n2 such that n and m greater than or equal to n2 implies norm fn minus fm less than 1 by 2 square. Now where will that n2 be? Well, I don't care where it is, I can always choose it to the right of n, because if it happens at some stage n2, it happens beyond that I could have chosen anything. So I can choose n2 greater than n1 such that this happens. Now you see this. Therefore, in general, epsilon equal to 1 over 2 to the k I choose, there exists nk greater than nk minus 1 such that n and m greater than nk implies norm fm minus fm is less than 1. Okay, so that now I keep on repeatedly applying this Cauchy-Ness and shrink epsilon slowly diagonally, and for each one I get a stage beyond which that error is attained. I can control it within that stage. So let us choose an nk. Okay. So look at fnk. Where is fnk plus 1? He has to be somewhere here, because that is the nk plus 1 state, and nk plus 1 has been chosen to be greater than nk. Now, if I choose n equal to nk, nk plus 1 and m equal to nk, and look at this, what happens? N is nk, so it is greater than equal to nk. M is nk plus 1, that is also greater than equal to nk, therefore this must hold. And therefore this will give me norm fnk plus 1 minus fnk, weak norm is less than 1 over. So now I have chosen a sequence of integers n1, n2, n3, n4, etc. such that if you look at the f of two consecutive ones in this subsequence, the norm is difference is less than 1 over 2 to the k. Is that clear? So this is what is going to help us in constructing the f. So generally we need not physically say that
Fn converges to f almost just Fn converges to f means that
First of all, I will get hold of that. And therefore, in this space, as long as I work with the function which is defined almost everywhere, I am done. And therefore, I will take the equivalence class generated by the graph, etc. So all that is understood. Okay, I have to, therefore, I have at least almost everywhere convergence. Anything less than that will not work. So now here I am not talking about LP convergence. Here I am talking about point-wise convergence. So listen.
for LP you need not say that.
I don't have to say that.
Convergence means that.
No, convergence means this. And that may not mean point-wise convergence, that may not mean non-wise, almost everywhere convergence at all. LP convergence doesn't have anything to do with point-wise convergence. We may not have any point-wise convergence, not even almost everywhere. So now I am going to cook up slowly. There is a hidden thing in this, which is a property of complete non-linear spaces, and that is being repeatedly rewritten here. Some books may first of all state that theorem in non-linear spaces and get this result. Okay. Anyway, that doesn't matter. So now look at now I am getting a little bit into point-wise fellows. There is a lot of confusion. Where is G defined? Now, after all, these fellows defined only at almost everywhere, because they are all elements of LP, and therefore their values are only under control almost everywhere. You could have you can measure with their values at a set of measure G. Similarly, Fn case, all these fellows can be measured, but all of them are measure 0. Throw away a countable number of sets with measure 0. You have simply stolen away only a set of measure 0. So still, this is a almost everywhere well-defined function. So this is well-defined almost everywhere. Now what I said, that's enough for me. Because if I want to get hold of eventually a function in LP, almost everywhere is enough for me. Okay. So I throw away that set of measure 0 where all these Fn x's are not defined. Only that remaining portions I take. Now what can I say about this Gn x? First of all, they are all nothing. Because there are some non-negative quantities are added. So Gn x is equal to 0 for all x. Now I will not write this anymore. The second thing is Gn x Gn plus 1x is greater than or equal to Gnx. Why? Because I am adding one more non-negative term, that's all. So therefore that may be 0 or something possible. So therefore if I fix this x's where all these things make sense and look at this sequence Gnx, it is a non-decreasing sequence. Right? Now it is a non-decreasing sequence of real numbers. I have fixed x and I look at Gnx. G1x, G2x, G3x, G4x, that's a non-decreasing sequence. If you have a non-decreasing sequence of real numbers, either it will converge to a real number or it will converge to plus infinity. One of the two must happen. The least upper bound is a real quantity, otherwise it goes up to plus infinity. So therefore, limit intended to infinity, Gnx, which is what? That infinite series. That is the partial sum, exists for all x, again, wherever that is defined, may be plus infinity. That will be an extended real valued function. Okay. Now, use non-negative function. So we can use Paul's lemma. What does Paul's lemma say? Integral of lim inf of Gn over omega dv is less than or equal to lim inf of integral. Okay. Now, what is lim inf of Gn? Okay, I want a little bit better, so I will do it, and not just GNs, I know what I want, so I will if I have gone through this and backtracked and come to that. Since I know what I want, I will do it. So now, what is happening here is the following. So at least let us look at where are these GNs. This is measurable, that's measurable, all these measurability is automatically taken care of. Now, this is an LP, this is an LP, right? F and Ks are all coming from that original sequence. So they are all in LP. Difference of two LP functions is in LP. So every term here is an LP. Finite number of LPs. So Gn is in LP. So Gnx, let me write that for. Because LP is a vector space. Finite number of LP vectors added is equal to LP. Secondly, we have since GNs are all in LP, I can talk about its norm. Now I have Minkowski's inequality. The norm of a sum is less than or equal to the sum of the norms. And therefore, I get this is less than or equal to summation k equal to 1 to n. I get that. This is Minkowski. That it is a norm. Sum of the norms is less than or equal to the norm. Norm of the sum is less than or equal to sum of the norm for finite fellows. Then, but what was our construction? That is less than or equal to, each one is less than 1 over 2k. So this is going to be less than summation k equal to 1 to n, 1 over 2 to the k, which is certainly less than 1. The geometric series 1 by 2 plus 1 by 2 squared, etc. etc. And therefore, it says Gn is in NP. Non-GNP is less than 1. What does that mean? That also is less than 1. To the power of 1 over p is less than 1. So raise both sides to the power of p. So integral GNP is less than 1. So now I will realize this. Now of course, one must really correctly look at this, but then this is much easy to make. You can see these things coming. If you manipulate, if you are familiar with this manipulation, so they are established. Now what happens is, I have Gnx, convert this to Gx, therefore Gn to the power of Px, convert this to Gpx, and Gn non-negative, therefore Gn power of P non-negative. So let us consider Hn as Gn power of P. Then Hnx convert this to G power of Px, and Hnx greater than 1. Okay. So I have a sequence of functions which are non-negative. First of all, forget about all this. I have a sequence of functions which are non-negative. Apply Vittal's lemma to Hnx. First, let us write that. What does that say? The limit of Hnx d mu over omega is less than or equal to the limit of omega Hnx d mu. Now I am going to look at each one of these sides separately. Now since Hn converges to g to the power of p, lim inf is the same as the limit which is g to the power of p. So integral g power p d mu is less than or equal to this quantity. But what is this quantity? That was this hn x gn to the power of p, and integral gn to the power of p are all less than 1, so the limit will be. So what does that say? That says g is also in LP, because p power is g is in. Gx is non-negative. That's what. Remember, Gx is the limit of non-negative quantity. The unit is non-negative. So I don't have to worry about the modulus. So I have now. Let's observe therefore. Gx is non-negative. Gx belongs to LP. That says Gx must be finite almost everywhere. Why? Because if it is infinite on a positive set of positive measure, that integral will be greater than that measure times infinity, which is infinity. So if it has to have finite speed integral and it is non-negative, then the function better be finite almost everywhere. For if A is a set that mu A is positive and g is equal to infinity of A, then integral g power p d mu omega is greater than integral A g power p d mu, which is equal to infinity times mu A, which is equal to infinity quantity. Because integral g power p d mu is finite. Okay. So therefore, what does it mean to say that g is finite? That means this series is convergent almost everywhere. G is that summation k equal to 1 to infinity mod fn x plus 1 x minus fn x. That means that series converges almost everywhere. Finite means that means that sum is finite, so that means the series really converges. This I wrote maybe plus infinity. That can happen only on the set of measure 0. So that means G, the infinite series, summation k equal to 1 to infinity mod fn k plus 1 x minus fn k x converges. I can now write like this. That is same thing as saying this series converges absolutely. The series without absolute sum says it converges absolutely means the absolute value series converges. We know when a series converges absolutely, it also converges. Okay. Absolute convergence implies normal convergence. So this series converges absolutely. Now what is this series? So what is the partial sum of this series? Suppose I take n terms. First one will be fn2 minus fn1. Second one will be fn3 minus fn2. What will be the nth one? Fn, I'll take n minus 1. It doesn't matter whatever you want. Maybe I should write that. What happened to this? This is gone, this is gone, this is gone, this is gone. I get just fnn minus fnn minus fn. Now, this series converges. Therefore, this column must converge, partial sum. If this column converges, that column plus fn1 will also converge. That plus fn1 is fnn converges. So we got hold of a subsequence of the original sequence which converges. Okay. So this is Snx converges and therefore Fnx minus Fn1x converges, which implies Fnx. And therefore, and what? Converges where? All these are only almost everywhere. Again there is a set of measure zeros to be thrown out because these places where Fn1 is not almost. So, the net result we have got so far is have these things but have variations. Hence, the subsequence Fnx converges almost. Pardon me?
The SNX.
Yes.
Yeah.
That is because with the absolute value, what is meant by if you have a series, this converges, then that also converges. That's what is meant by absolute convergence. So therefore, I have this converges almost. So now I have a way of getting hold of a function. So that fx is equal to limit infinity to infinity Fnx wherever this exists. And other places you do whatever you want. It is a set of measure zero. So define arbitrarily. Okay, this completes the first step. What was the goal in the first step? To catch hold of a candidate to which some subsequence converges almost everywhere. The second step goal is to show that the candidate you got is really the space where you wanted, not you have gone out of. So next claim, NPC. The limit that we have thus got is indeed NPC.
So this limit is still called unique.
Don't worry about anything. I am simply now doing a very wild thing. Finally, I catch hold of one fellow and I show that Fn converges to this in the LP sense. And if it converges in the LP sense, that must be the only fellow. If there is some other fellow, some other subsequence, some other fellow, that fellow must be the same with this fellow almost everywhere. That last step takes care of all this confusion that exists. Right now, I don't even know one fellow. So I caught hold of one fellow. You are worried about if somebody else. I will worry about him later. First, what I have got, I will establish all my things with that fellow. And once that is done, the rest of the fellows are automatically taken care of.
Yeah. However, we define F on that measure zero set. Still continues to be measure zero, right?
Yeah, right. Yeah, right. Definitely continues to be measured. Because that set is measurable with measure zero. So F inverse of any Borel set, if that thing consists of infinity, this set will be added to it, but that will be still of measure zero. It's a measurable set. What is important is the other part is measurable and has measure zero. That is not just how to measure. Function continues to be measurable. Because we have proved a theorem, if two functions are equal almost everywhere, then they are so you take it into 1 or 46 or 98, a constant function. That's measurable. Okay, so that's our, now we have our second step.
I don't think we have proved that.
Which one?
What we just know.
What did I say? What was it that I did not prove?
we have two functions, one is measurable. They are equal almost.
Yes, I have. Okay, check the videos. I think maybe notes I have not given yet, but you check. I approved that. But I would upload it as one of the earliest results. F is measurable, and F is equal to G almost everywhere. Then G is also missing. In fact, I drew the pictures also for the sets and all. So done in this room. But also I okay, so where were we now? We want to prove that the fellow whom we got is a first valid candidate. Our candidate must be in LP, otherwise we are not in business. So we got to show that F is in LP. So our eventual goal how we are going to show this? I want to show that that fellow is in LP. How I am going to show it is, this fellow plus somebody is in LP. And that somebody is also in LP. So the difference will be in LP. And therefore is in LP. So what we are going to show is, okay, we will see what is happening. So now again, Fn is recall given. So for every epsilon positive, there is an epsilon, so the exactly epsilon implies norm Fn is equal.
Okay.
So now fix m greater than 10. Fix m greater than or equal to 10. Any m. Okay? Fix any m greater than or equal to. Look at some phi n x be equal to anyway, I'm going to integrate, so I put as well as 3, save one step. Now what happens to this? This is now a sequence in n, because m is fixed. This is a sequence in n. What happens to this as n goes to infinity? This fellow remains as he is, because he is fixed. But as n goes to infinity, so that's let us look at this. Fn n m, whatever I should say, nm greater than epsilon. Now what happens to this as n goes to infinity? This fellow goes to fx. So this converges to mod fx minus fnm x. That's okay, because this fellow is fixed and not fixed. Then what happens therefore to, and phi and x are all greater than the because of the modulus there. So I have a sequence, non-negative, apply 40 to phi. Now what does it say? We mean for phi n, the mu is less than the min of phi n. What is this? Right? Because it converges, so it's only the limit, and the limit is that. This is less than or equal to, what is this? That can all be made small if nm has been sufficiently chosen far enough, because that is just the norm of this fellow. So this is less than epsilon to the power of p if nm is sufficiently large. That m is sufficiently large. Then what does this say? This simply says fx minus fnm belongs to n. But these fellows are all in LP. So this plus this also will go to LP. So fx minus fn plus fn also belongs to LP, because this is now belongs to LP, this belongs to LP, sum of two LP functions is LP, so LP. You have to choose this M sufficient terms. Now we are done, because this fellow again, this fellow again says that the norm of Fm minus Fm and okay, and a little bit more carefully, but we can that is this integral only will tell us and therefore Fm. Okay. Here you do bit of proper indexing, right? But basically what it says is this one fellow, this one inequality will take care of all the others. Moment you establish that F fellow is in LP, all this is permissible. Okay? Then this immediately tells this also is the same fact as the convergence. So basic step therefore is to get hold of a candidate. Now your question comes. Suppose, remember I chose the N1, N2 greater than N1. Suppose N1 was 100. Somebody would have chosen N2, maybe 126. Another fellow would have chosen is 246. So he is going to get a separate, some other subsequence. Now when he gets some other subsequence, he is going to get some other limit. So he is going to get an F tilde x. And he will say, my F tilde is the right fellow. And you are saying Fn is converging to F in LP. I am saying Fns is converging to F tilde in LP. But if a sequence converges to two different limits in LP, the two limits must be equal almost everywhere. And therefore again they are all united except for a set of measures. So that will be automatically. Okay, this is essentially the gist of the proof. Right, so therefore I am not looking at L infinity, I will come to L infinity later. Now, we have established the fact that LP is a Banach space or a complete norm linear space for one less than P. So from this stage onwards, essentially everything that we do on a nonlinear space or a Banach space can be done on LPs. So, in fact, these are all the concrete examples that will keep coming when we do functional analysis. All these LPs are now concrete examples. So, now I'm going to look at some little functions.
Regarding the measurable. So when function was infinite on the way of defining the Lagrange, we followed a certain procedure. That is, we took all functions less than this function, and those functions were bounded. For those, we took the Lagrange and look at all functions. Now. So here the case is that Gn it could be infinite.
Gns are
No, they could be infinite.
Gn summation k equal to 1 to n mod fnk minus fk. Fnk minus fk are all real valued almost everywhere.
So it could
Even
Gx,
if
Gx could be infinite.
Gx could be, limit could be infinite. Even fnks could be infinite, but they will be infinite on a set of positive zero measure and throw them all out right in the beginning. That's still a set of measure zero. So Gnx are finite almost everywhere.
Yeah. So the proof I'm trying to refer to is that we haven't done probably. For that case, when the function could be infinite, you fill in whatever value you want, and we follow the same procedure of finding the level. Then in the two cases that we
Because that set is measured zero.
have we done that?
Because how is the integral defined?
Because for infinite fellows, we have a different way of defining it.
As long as that's why I said we allow infinity only on a set of zero measure.
Yeah.
Extended real valued are allowed only in a set of measure zero. The moment infinity comes in a set of positive measure, then we allow either plus infinity or minus infinity. If plus infinity comes in a set of positive measures, the integral is plus infinity. If minus infinity comes in a set of positive measures, the integral is minus infinity. The supremum and infimum become plus or minus infinity. But if both occur, if there is infinity on a set of positive measure and there is infinity on a minus infinity on a set of positive measure, then integral f plus will also be plus infinity, integral f minus also will be plus infinity, and when both are infinities we don't define the integral. That's how we did it. Yes.
When the function takes...
Okay, let me explain to you. Suppose a function takes infinite values. Okay? Suppose a function takes infinite values. Now take infinity into suppose you take constantly infinity everywhere. Right? What will happen? The integral. Infinity. Right? So now if you have only on a set of simple measure, divide the integral into two parts. One where it is finite, the other one where it is infinite. Suppose that infinite thing is positive measure. Now we have a simple function where the finite part is approximated nicely and the infinite part I take it as infinity only. Then what will be the integral of that simple function? It will become infinity. Now look at the supremum or the infimum, whether you come from below or come from above. And that will tell you the integral has to be defined as plus infinity. The moment you go out of a set of zero measure, the integral is forced to be infinite. That has to be the only way to be defined, even if you take carefully go through our definitions. Okay. Or if you want to take a function from below, take phi nx to be n on that set. Okay. Then the integral of phi n will be n times that measure, n mu a. And as n goes to infinity, that will go to infinity. So the integral has to be defined as infinity. So suppose you have fx. Fx to be infinity on a. Suppose you have fx equal to infinity on a. And you look at phi n equal to n on a. Don't worry about other step. That is more nicely taken care of. Now phi nx is less than or equal to fx. So it is n times chi a. It's a simple function. Now phi nx is less than or equal to fx. Now the integral of phi nx is n times the measure of a. Measure of a is finite. Okay. Now what will be the supremum of this? It will be infinite. Therefore, you have to define the integral as because you take all simple functions which are below, take their integral and then take the supremum. So the supremum has to be defined as infinity. So the integral has to be defined as infinity. You have no alternative. That very definition says it has to be defined as infinity.
My question is actually for the case when it is infinite only on set of measures below.
Then there is no problem. The very definition is this. Measure of a is 0, then you define the integral to be 0. That's it.
So it's saying there is a measure zero set on which the function takes infinity.
There is a measure zero set on which the function takes infinite.
Yes, look at that same example and see what happens. Look at the same construction and see what happens.
No, it's probably a case of we know the result.
So here is a sequence of, what is this integral of phi n now? If your measure a is 0, right? Integral phi n will be 0. Now here is a sequence of non-negative measurable function monotonically increasing, apply monotone convergence here. So integral f1 must converge to integral f, but integral f1 converges to 0, and therefore integral f has to be defined as 0. So monotone convergence theorem will take over. Okay. Whatever way you look at, you have no alternative. If it is in a set of measures, if it is a set of measures 0, you have to define the integral as 0. If it is a set of positive measure, you have to define the integral as plus infinity. If it takes plus infinity value on a set of positive measure, minus infinity if it takes minus infinity on a set of measures 0, And you say the integral is not defined if it takes both plus infinity and minus infinity on sets of positive measure. That is why we say if integral f plus and integral f minus, if one of them is finite, then we can define the integral. That's how we do it. Okay?
Sir, it is not.
Yeah.
LP spaces. Yes. With our omega is an abstract space, right?
Yes.
So we are what we are saying is the inverse image of f now as omega to r. So the inverse image of any
Borel
set
set.
belongs to the Dickmann set. That's all we are saying.
Inverse image of?
Of a Borel set,
Yes.
the real line,
Yes.
belongs to the
That-
Dickmann.
That new measurable set.
That's all. we are
That's all,
saying.
yes. And measurable simple functions are defined accordingly and everything is taken.
So in this abstract setting, LP is
Complete. Yeah. LP omega B mu is complete. Whatever be the set omega, whatever be the sigma algebra and whatever be the corresponding measure. LP omega B mu is always complete. Any abstraction. There's nothing to do with the real line, the Lebesgue sigma algebra and the Lebesgue measure. If you are taking an abstract, for example, omega could be a probability space, B could be the sigma algebra of all events, mu could be a probability measure, then LP omega P is complete. Whatever was your probability measure and whatever was your sample space and whatever is the collection of your events, in that setup, that will be a complete space. Okay?
Sir, roughly, what are the kind of omega for which Lebesgue procedure of finding the outer measure and then getting the...
You see, first of all, Lebesgue starts with intervals. Okay. Already has a very strong structure of the real line coming into this picture. One way to avoid it is, one way to generalize it, you look at a metric space. Okay. So a priori, if you know how to define the measure of a ball, open ball, okay, then start from there. Define now the outer measure as any set in that metric space which can be covered by a countable number of open balls, and define the outer measure as the sum of all the measures of these open balls. Then go through the same Ramayana again. We have the outer measure, show that all these things are valid, and then define the measurability criterion. You can do practically the whole ball game. That's how we do RN. That's how we do in RN or anywhere we can do. So there is various ways of doing in RN, because we have the advantage we can write RN as R cross R and look at in a different way. But that is also done. That construction is also done. Take a metric space, a priori give you the notion of how do you quantify open balls of radius R, and then from there construct the whole measure gamut. So what is the general thing about it? The way to generalize this whole outer measure construction is, to start with, you must have some standard weights. Lebesgue at intervals, you could look at the balls in the metric space. If you have an abstract set, there are certain elementary sets for which a priori quantification is given. And that a priori quantification should be such that it's non-negative. If I take elementary sets and take their union, if it turns out to be an elementary set and all the laws are valid, once you do that, now if you, whichever fellows you can zoom on from outside by these elementary sets, define outer measure, go through the same number. So it's not the interval, it's not the ball, it's not that thing. There is a certain type of standard weights that are available for you. They obey the standard laws for weights, and once you have that, the whole thing gets triggered off. Nothing is left over. After that, it's the whole ball game. Because everything is set theoretic afterwards definitions. We go through algebras, then we go through sigma algebras, all those definitions come. So this whole construction can go through. In fact, that is exactly what Norbert Wiener does when he constructed the white mass. As Wiener measure on the space of continuous functions. What he does is he wants to define a measure on the space of continuous functions. So his points are no longer real numbers. Every point for him is a trajectory, is a continuous function. Now he says, I will take special subsets of continuous functions which play the role of real numbers. I will now assign a measure through the Gaussian. Now this obeys, now I have got hold of standard weights. Once I have got hold of the standard weights, I will go through the Lebesgue construction. I will get a measure on the space of continuous functions. And that is what is called the Wheeler measure. His cleverness is the following. How do I construct the standard weight on the space of continuous functions? No, he goes by, Norbert Wiener, once you look at what he does, it's very simple. There is nothing sensational about it. He says, now we look at a cylinder. What is a cylinder? They have got various ways of looking at it, geometry, etc. Now, after all, I cheated you by drawing a cylinder with circular base. Could have been any base. That's still called a cylinder. Could have a cylinder with a rectangular base. That's what I call a rectangular parallelepiped. Now, basically, geometrically, what it is? See, any point in space has 3 coordinates. Right? Any point in space has 3 coordinates. Now, a cylinder is some kind of a structure for which we are given some restriction. Say, cylinder with circular base. What we are saying is, I don't care what is the float of that second, third variable. The infinite cylinder is what? Is something where certain variables are restricted. Certain variables are restricted. And particularly if I have a rectangle based cylinder, which is a box, it is something like A less than equal to X less than equal to D, C less than equal to Y less than equal to D, and I let the Z variable. Or if I want to tilt the cylinder in this direction, I can give restrictions for X and Z. And so, suppose you are in n dimensions. Suppose you are in n dimensions. Then, for me, a general cylinder set is set of all points such that some r coordinates I give restrictions. Like this, here I gave for 2 coordinates restrictions that they lie in some interval. So I bring in that interval somehow. So what I do is, I give restrictions on certain coordinates. So it may not be first and second, so I1 coordinate, I2 coordinate, IR coordinate. And now, if I can define what is the general then in the setup of the space of continuous functions? What Wiener observed was, I can interpret this as a discrete function. x1, x2, xn. It is defined on the discrete set 1 to n. Now when I am having a continuous function, that's a vector. That's one point there. If I have a continuous function, I am having a continuum measure. Okay. So here I put restrictions on a finite number of coordinates. There also I will put a restriction on finite number of coordinates. Something like, I am going to look at all functions ft which are continuous etc. such that ft1, a1 is less than equal to ft1 less than equal to b1, a2 is less than equal to ft2 less than equal to b2, ar less than equal to ftr less than equal to b. So I will take continuous function which satisfy this condition. I will call such a thing as a cylinder set in the space of continuous functions. That's all. Huh? AIs are some fixed number. Now I can vary T1, T2, TR, I can vary A1, A2, AR, I can B1, vary B1. So the typical cylinder set is like this. Now he says how to quantify such a typical cylinder set. And that comes from the Gaussian. You integrate the Gaussian, the R-dimensional Gaussian over this cylinder. Okay? You integrate the R-dimensional Gaussian with this R-dimensional cylinder. Only the other coordinates will give you value 1. Okay, so then you got a measure. And once you got this measure, and it becomes a probability measure because everything is brought under less than or equal to 1 by adjusting the constant 1 over root 2 pi sigma, etc., etc. Then you got a quantification of certain types of sets in the space of continuous functions. So you take C01, in the space of all continuous functions of 0, 1, consider such sets. These are all called cylinder sets, and you define the measure of these sets by integrating the R-dimensional Gaussian over these sets, and that gives you a sort of standard ways. Now go through Lebesgue construction. You got Wiener measure. That's all there is to white mass construction. So once you know what really is going on in the normal measure, the rest of the thing is the same thing we brought in that, convert it to this language and do it. The conversion is to see how you do this.
So, but on the real line, any set can be covered by some finite number of open intervals.
Yeah.
That's why he took that question.
But here also you allow me to vary the number of points. See, I put minus infinity less than T1 less than infinity. That whole thing is a cylinder. See, in the real line I said every set can be at least one open interval cover, namely R. Here also, the whole space can be thought of as a cylinder, like I am putting one condition on T1, namely minus infinity less than T1 less than infinity. That's obviously satisfied. Okay, so that is, you have a class here?
This class will be?
I finish at 12:30, but you want to use this room?
12:30.
Huh?
12:30.
Yeah, right.
Okay, then I don't want to.
Okay. So, there is always one cylinder set, namely the whole space. That is the whole plane has to be treated as an infinite cylinder where all coordinates, everything is freedom is available. You look at it that way. And the measure is 1. Because you now integrating the Gaussian over all the whole space, we are going to get 1. So that's why the total measure has already been made to 1 by his construction. Is that clear? That's the rough idea of what you mean. Pardon? Such cylinder sets only. I mean, once Wiener gives it today, that's all we go on doing it again and again and again. We look at it. Generated by these fellows. And then we can. No, first of all, what you do is, you don't look at actually the sigma algebra generated by these fellows. You look at the outer measure generated by these fellows, and then look at the measure generated by the Paracel precondition, and the measurable sets form a sigma algebra, and that sigma algebra is the Wiener sigma algebra, on which you have the Wiener measure. Okay. That is a normal construction. Everywhere you have to, whenever you have a continuum of functions like this, you have to look at cylinder sets, which is suggested by what is a cylinder in the normal. Cylinder is essentially a collection of points in the plane in space where restriction is put on certain finite number of coordinates.
This is one convenient way of coming up with a measure.
Pardon me?
This is one convenient way of coming up with a measure.
Yeah, that's all. Because you see, for example, Wiener, even to get the standard measure, what did he do? He used Gaussian. Why should I use Gaussian? I could have used some concocted measure which gives me total 1. And still worked with it. There is nothing. So Wiener chose a very specific measure for this cylinder set. So on the same set of functions, like on the interval, why b minus a? I could have chosen a non-decreasing function and then looked at continuous non-decreasing, to be simple. fb minus fa as the measure of that interval, standard weight, and then constructed then I will get Lebesgue-Stieltjes measure. So one gave me the Lebesgue measure. Similarly, Gaussian gave me the Wiener measure. I could have done a lot of other things here and got different measures on the space of continuous function. But somehow or the other, everybody likes Gaussian. And yeah, okay. So otherwise I get into construction of those things. That's roughly the construction, always. When you have a collection of functions, which could be random maybe, collection of functions. What you do is put restrictions on certain time. Okay. So all your stationery, all kinds of the fantastic terminologies will come. You put certain restrictions on certain time samples. You sample at certain number of points and put some restrictions on those samples, and then build up your cylinder sets and then build up your mesh. This is the standard construction which Wiener does. Okay. Which Wiener saw how this whole conception of method could be lifted up further to the space of functions.
Giving that outer measure projects.
Yes.
I remember you mentioning that you need some notion of compactness.
That is to prove that wherever that certain things are there, certain small additional hypothesis will be put. But that's not a very big deal. See, we showed, what did we show? We wanted to show that the outer measure of the interval was exactly what we started with the length. So there will be a similar result that will have to come here. The outer measure of the elementary set you started with is the original measure you started with. All these things will be taken care of as you go along in the construction. But major line of thought is essentially the same. Nothing. The one problem with the real line we had was, we had this interval, we had left close, right open, right close, left open, all these intervals are the same length, all kinds of things we wanted to show. And we don't want all these elementary sets. Some or other elementary sets will have the same outer measure as the original thing you started with, that's all. So that will all be taken. Okay. So if you just look at Wiener's construction again, you see now the cylinder sets coming in the equilibrium. Okay. So now I have this, I want to make certain, now that I have shown that the LP space is complete, I will as well look now, which is a nonlinear space, it is complete. So first I will look at some things about non-linear space, and then we will talk about what special effect you get if we are complete also. Now the first thing that I want to observe is the following. Suppose,
Just a last one.
yeah, go ahead. Go ahead.
Why don't we write that other mu also when we write a LP space, saying that omega p mu is a measure space.
Yes.
But there is one another mu which will play a role obviously in all those.
Which other mu?
On the subsets of omega.
I didn't understand the question. Now what?
For f to be measurable,
Yes.
starting with any.
Okay, let's see. What do you start with? I have said omega. Then what do you do?
Then we have b.
B.
Collection of subsets of
Sigma omega.
yeah.
Okay.
The last mu we write.
This is the vector space.
On b. The r thing.
The mu is with respect to it's only when it is on acting on P, it is a measure. To try to get outside, it's gone. So the mu says, where am I working? That's why we simply write. In fact, most people write LP mu. Understanding what is the set and the algebra is taken care of, only the measure is the important thing there. Okay? So now let's take a non-linear space. Now suppose for a moment we did not worry about the norm, we had only linear space. Suppose I had a linear, that is a vector space. So suppose I had known only vector spaces. Then I look at, let us say over C complex. We have taken real or complex vector space, doesn't matter, let's write over this complex. Any such function which assigns with each vector a number is called a functional, right? a map is called, that is functional. So if domain is X, codomain is C. Now whenever you have certain maps on vector spaces, we are interested in those maps which preserve the structure of the vector space. What do we mean? We do two things in a vector space. Namely, we add vectors, we multiply a vector by two scalars. So I have two vectors, I add them. I could also multiply a vector by alpha, some number. So now I want to see the effect of F on this. Now, if it preserves addition and if it preserves multiplication, what does this mean? I superpose and then take the image, or take the image and then superpose, or scale and take the image, or take the image and scale. It should come out to be the same. It's nice for me because even if I had forgotten, I can do things right. Such a thing is called mean for all alpha for all. Then F is said to be linear. Okay. Now I come here. I have a nonlinear space. Again, the linear part of it is over C, complex nonlinear space. Scalars involved are complex. Again, I look at right. I am looking at functions from X to C. Again, I see what are all the ingredients in this space. Because it's linear, those are already there. So I want this. So then we will call it as linear function. That's no problem. That comes from exactly. I am not even worried about it. That this part alone gives this definition. It's a linear space. But now I have an additional structure. The norm is into the picture. I want the basic structure induced by the norm be also preserved. Now you may say that norm of fx must be equal to norm of x. You may say I take the image and take the norm. What is the norm on the complex side? This must be equal to take the norm and take the image. Does it make sense?
No.
No. So this is not a correct question. Okay? Because I don't know what is meant by f of norm x. I know only f of a vector. So that doesn't make sense. That's not the right question. So that is not what the structure we are asking for. So what is the structure we are asking for? What is important with the norm is, the norm induces a metric. And the metric induces the notion of continuity. You have a notion of continuity in a non-linear space. So what is continuity? If xn converges to x, we have a notion of, we say xn converges to f if for every epsilon there is an epsilon, there is a delta greater than 0. Okay, even let me take convergence. First of all, there exists an epsilon. That is the that's the notion of convergence. Instead of modulus, now we are putting norm. That's the only difference. So therefore, what we are asking is that the convergence be preserved. That is, if xn converges to x in this norm, in this space, then where is their image? Fxn is a number Fx is a number, that number must comply with the norm. That is, you take the images and then take the limit, or take the limit and then take the image. Both are going to be the same. If xn converges to x, fxn must converge to fx. This is an additional thing we would learn. This we will call as continuous linear function. This is called continuous. So what we are saying is, whatever is the structure this side, we preserve when you make this translation into this number language. Okay? Things be done in a smooth manner. So in a normal linear space, we have only the notion of linear functionals. In a non-linear space, normal linear space, there is this continuous linear functions. So this is what is of importance in a non-linear space. For study in vector spaces, we study only linear functions. Okay? The so-called dual space there, when they say algebraic dual, they talk about only linear function. But here we are talking about a topological dual, which is a continuous linear function. It may so happen that there are linear functional which are not continuous. We will see examples. And therefore, if you are doing only algebra in this, you will not worry. You will take into consideration them also. But when you are doing topology, then that's not interesting. I am interested only in continuous linear function. So there is a topological dual and the algebraic dual. These two are totally different. Okay. Algebraic dual is much bigger because it allows discontinuous linear functions also. Okay, so now I am going to make one small observation in non-linear space. Yeah.
So f where does it belong here?
Pardon me?
Is it in non-linear space function f?
Yes.
Where does it belong?
Which one?
That f mapping from x to
See, f is always associating a vector x to a number c. I am considering this a norm. F is a mapping to one. F associates a number with each. It takes every vector and associates a number with it.
whether it belongs to LP space or something.
There is no question of LP here. There is no measure. I am not at all talking about a measure. I am talking about a general nonlinear space.
So I am confused with if you say that f is a mapping from x to c.
Yes.
If domain is x.
Yes.
And f, the property of the f should belong to some function space, right?
I am not at all talking. I have no function space. The function space is this, whose domain is x, is domain is c. That's all. It's a complex valued function defined on x, which has these properties. Right? Now let me give you an example. I have R3. That's a vector space. Right? Now, or even C3 for complex number. Suppose I have a complex number vector space. I define, what does this mean? With each 3-component vector, I must associate a number. Right? So I simply say, associate with this the number say x1 plus x2 plus x3. Simply add up all the coordinates. That's a function line. With each vector it associates a number. So what's the confusion?
So actually I am confused with the function space. What do you mean by function space?
So function space is a collection of functions with some domain and some codomain. That's all. Yeah, right. What is the function space? F belongs to the collection of all functions from C3 to C. It's a collection of all functions from C3 to C. That's all. That is the function space to which it belongs. Yeah, you don't confuse with LP. LP is gone. Now I am looking at a general nonlinear space. Okay?
What I was confused is if you say some mapping from one domain x to c, we should specify where does that belongs to. That completes
No. First of all, you must specify what is F.
Yeah.
What is F? This is F. With each vector it associates a number. Right? That's all. Now what I do is, what does it do? Here is a vector space, I will call it as X, and here is the complex number, C. What does this function do? It takes a vector X and associates it with a number. Okay. Now, this is the notion of length given by the norm. The original vector had a length. It has been transformed, and the transformed vector has a length, which is mod fx. It's a complex number, it has length mod c. Now, this was the original length, this is the new length. I do some kind of elasticity, when we do what is strain, you look at the ratio of the new length to the original length. That is some kind of an estimate of what sort of damage F can do to metric properties. How much damage it could do probably with the length at that point. Now this will vary at each point. Different points that the ratio will be different. Now I want this to be under control. That means it should be within some elastic limit. That is, suppose this is less than or equal to k for if every x belongs to this. Now there is some mess here. I have put x in the denominator. So if x is the 0 vector, I would have put 0 in the denominator, and that will be 0. I will have 0 by 0. So let us put x not equal. For every non-zero vector, if this damage that is done within some elastic limit k, some Hooke's law is there, then we say, then therefore the supremum is very different. It's not bounded, it's bounded, therefore it will have a least upper bound. And therefore that supremum is well defined, and that is a measure for that functional f. That is a quantification of that functional f. You go and look at each point what sort of elastic damage it does, and look at what is the maximum elastic damage it can do, and that is a sense of quantification of that functional f. And in anticipation that has been written as a norm because it is going to be a norm in some sense. Okay? Or if you don't like it, we will call it as a number which depends on f in f. And nf is finite. Because such, it may or it may not happen. The damage may be so much that the space may be torn and the damage may be phenomenal. And therefore, if this happens, we say little f is a bounded linear function. So if this happens, and put all the definition properly next time, if this happens, we say f is a bounded linear. So I have a linear functional, continuous linear functional, bounded linear function. Any question?
So the set x where you can set x on which we are operating x. That number will be changing for the subset on which we are operating.
No, I have a fixed nonlinear space and I am now looking at maps on that nonlinear. Okay. Now for each vector x in that nonlinear space, I see what is. So I have my elastic medium. That's the x. On that elastic medium, this f is going to act.
If we restrict f to some subset of x, then that number will
That may be different. That is a different ballgame altogether. That is a different. So in other words, you are not looking at the entire medium, you are looking at some small place. That is a different ballgame. You see, it may do decent damage here, but terrible damage in the other place. Right? tsunami may hit Kadalur more, but Bangalore is unaffected. That's a different ballgame. We are looking at globally the damage done by that function is defined on the whole space, and we are looking at the functional as its action on the entire space, not restricting. We will look at the restrictions later.
So that number doesn't really relate just to x, but it's dependent on the x.
Yes, but I have fixed x, so that's why I am not writing that again and again. Now I am going to fix that linear space, and I am going to look at various f's on it. X is fixed, the norm is fixed. Once these two are fixed, that medium is fixed for me. Now on that medium I am going to punch with various functionals. I am going to look at these various functionals. So I have now, therefore, because what is a linear functional on one x may not be a linear functional, may not even be defined on another x. So these things have to be fixed first. The domain, the codomain has to be fixed first before you talk about the function. The moment you are changing the domain and the codomain, you are talking about functions in different universes, isn't it? So now the interesting thing is, f is bounded is the same as f is continuous. Bounded linear functional is the same. For linear functionals, the notion of boundedness and continuity are synonymous. We can show that. Okay. So invariably we will say either a bounded linear functional, or sometimes we will say continuous linear functional. But when we say continuous linear functional, we will go on using the fact that it is bounded. And when we say bounded linear functional, we go on using the fact that it is continuous. They are synonymous terms. That's a small reason. Now what happens in the following? And just make one comment. Let us come back to this C3. What is the dimension of that space? 3. So you can choose any basis. Okay. Let us take any 3 linearly independent vectors will form a basis. Okay. So therefore, if we take any vector x in C3, x will be of the form x1 e1 plus x2 e2 plus x3 e3. It can be written as a linear combination of the basis vectors. Now suppose it is a linear function. Suppose it is a linear function. Then f of x can be written as f of the superposition is the superposition of the f because it is linear. So I can write it as x1 fe1 plus x2 fe2. Now let us look at the following situation. The vector space is given, namely C3. The basis is fixed, right? And the functional is given. So the vector space is given, the basis is fixed, and this f is given. Right? The moment the f is given, this can be found out, this can be found out, this can be found out. Because E1 is known, so Fe1 is known, E2 is known, Fut is known, E3 is known, Fe3 is known. Suppose. The moment that is known, give me any vector x. The moment the vector is given, these numbers are known. This component with respect to basis should be known. The moment these components are known, this entire expression is known. That means the moment you know these 3 numbers, you have completely known that function. Okay. So therefore, f is completely, I will just write it as completely determined by its action on E1, E2, E3. That is, by the three numbers FE1, FE2, these three numbers determine completely that function. See, the whole space, I don't have to go on seeing what is happening here, what is happening here, what is happening here. If I know what is happening at three basis vectors, practically I know what is happening everywhere here. That is the advantage of linearity. Now, I define a vector F, I call it a vector F to be formed by these three numbers. FE1 bar, FE2 bar, FE3 bar. Then what is f of x? F of x is simply the dot product of x and f, the complex dot product of x and f. Now essentially what this says is all the linear functionals can be identified back with the vector in C3 itself. So if we now look at the collection of all linear functionals, I see their reflection, I see their images. There is a way of getting their images on C3 and we can completely identify it with C3. For every linear functional there is an image here and for every fellow here there is a reverse image there. And in other words, the study of linear functional boils down to again studying the same vector space in this situation. This is a typical situation in finite dimensional space. The dual is like a alter ego. Every space has a dual which is the same person essentially in a different language. Okay? So C3, the linear functionals are nothing but C3 itself written in a different language, that's all, or vice versa. But this is not so when you go to infinite dimensional space. Things become very complicated. And when you go to non-linear spaces, we would like to say, here I have continuous linear functional. Just like I got a neat concrete representation of these fellows, is there a neat concrete representation of these functionals also somewhere? And all these LPs fellows have a neat concrete representation of functions. They may not have, see here is a very typical situation of a Hilbert space where the image falls on itself. Now what will happen is, I have a vector space, I have a non-linear space, there is some other space which is its dual, which is the collection of continuous linear functions. Then that will be a non-linear space. Then the ball game will start. What about its functionals? That will be another space. And then the ball game says, what about that fellow's functional? Now this game will go on. But often there are certain very nice spaces where in the first reflection itself it comes back, or in the second reflection it comes back. If the first reflection it comes back, it is a Hilbert space expression. It is the second reflection it comes back, it's called the reflexive Banach spaces. And these are all very nice spaces to work. I will look at that. And then look at it in the context of LP spaces. Okay? And essentially, these are the main results that you will have to know.